Sup, you dead? Hey guys. Do you know what? This is going so well. I've got all of you guys rocking up. It's ace. We've got Rue, we've got Shan, we've got Moses, we've got Harris, we've got Anna, we've got me. There's me. There's Ruby. Got Andy. Got Toby. Got Tom, got Ashley, got Ben. We're smashing this today. This is amazing. There's Ashley. Whoop, whoop. Is Kieran here yet? Where's Kieran? There's Isabel. Yo, Isabel. I'm like the coolest person I know. Like I'm just getting cooler by the day. I'm gonna be liquid nitrogen cool soon. That's how cool I'm gonna be. It's gonna be amazing. Got Ben. Yeah. We're missing Kieran. We're missing Yura. We're missing Wen and Con. Victoria's not here. Yeah, there's Elijah. Yo, Elijah. Good to see you, dude. Thanks for coming on to my Year 10 lesson. That's good. We're doing moles today, Elijah. It will be very beneficial. Has anyone seen Nick? Where's Nick? Come on, Nick. Hey. We're doing well. Who's that guy? Got Victoria. Whoop. Yeah. There's Nick. Yeah. I can't believe Kieran's late. Can you believe this? Sheesh. Oh, can you believe it, guys? Can you believe it? Best lesson of the day. And Kieran's late. Kieran's watching. Oh. But can't type. Nice. Oh, thanks, Kieran. We're missing Yura. Okay, we're missing Yura. We're missing Con and Wen. But I'll kick off now, folks. Whoop, whoop. Yeah, let's kick off. Okay, so I'm going to share my screen. We can crack on. I hope you guys all had. Let's do share screen. And then let's go, yep, there we go. And then do that one there. I don't want my horrible face on there. It's like that. And then I'm going to disable my camera because if I disable it, it gives me a little bit longer before shaky screen problems. There we go. Cool. So guys, this is our lesson today. So we're starting the dreaded moles. It's going to be very exciting. I'm going to get rid of my keyboard. See if I can get this thing all sorted. There we go. Yeah, we're getting there. Okay, so today's lesson, we're going to be starting moles. He's not logged in. Okay, Kieran says hi. Hi, Kieran. Okay, so the first thing I want to do is just quickly go through the homework that I set you guys on combustion. I gave you guys a couple of equations to do. I thought it was really good practice for you guys to have a go at these, partly because it's a reminder of what you're doing in Year 9. I know that I think I put the answers up. But I'm going to go through them now. If you haven't had a chance to have a go at them, please do so in your own time. You can even pause the video and have a go now if you wish. Wouldn't make an awful lot of difference. Okay, question number 1, the complete combustion of methane. So we've got methane. We're going to have to remember CH4, 1 carbon for methane. We have to add in oxygen, and it said the word complete. So that's telling us what our products are going to be. We're going to get CO2 and water. This is maximum energy output, which is great. Now I've just got to remember to balance it. Did it ask me for the word? Write a word equation, then a balance symbol. Okay, so the word equation will be methane. Methane plus oxygen goes to carbon dioxide. Carbon dioxide plus water. So there's the word equation. But of course, words is not laggy. Oh no. Is it laggy already? I'll see if I can make this thing go a little bit faster. Oh, I can't. It's already maxed out. I apologize if it's laggy. I'm just gonna, if I just play this, I'm just gonna see how laggy it is on my end. I wonder whether or not, mine seems to be okay, Kieran. Mine seems to be all right. I wonder whether or not it's yours. I don't know. I don't know. Have a go. I think it's me. I have bad Wi-Fi. Okay. Thanks, Nick. All right. So now we've done the word. We're going to go symbol. We changed the symbol and we're going to balance it. So 1 carbon, 1 carbon, 1 carbon, 4 hydrogens, 2 hydrogens, double it. 4 hydrogens, 4 hydrogens. Now we've got to do the oxygens. We lost the H. So we've got 2 oxygens. We've got 4 oxygens. That's the key thing to that one. There we go. There's the first one, number 1. Number 2, let's try and be as quick as possible. Incomplete combustion of octane to produce carbon particulates. Okay, so word equation, octane plus oxygen, nice and quick. Oxygen goes to, and it was carbon particulates, carbon and H2. No, word, not symbol. Yeah, so carbon and water. We always get water, always, always. Then we go C8H, double it and add 2. 16, 18, it takes me a bit of time. 2 plus O2 goes to carbon plus H2O. Balance the equation. Balance the equation, need to make that disappear. There we go. So 8 carbons, 18 hydrogens. Put a 9 in front. Right, oxygens, 9. That's awkward. That's going to be 4.5. Right, you can't leave halves on there. The only time you can use a half, by the way, is when you're in an element, and that's an oxygen because it's an element. Winter is here, but she can't type. Okay, thanks for letting me know. I'll quickly do the register for that. That's nice to know. Thanks very much. I'll add that in. Nice to see you. Tell Winner, say hi. Oh, hang on. She's going to hear me. I'm an idiot. It's fine. It's really funny. Okay, so I'm going to double everything to get rid of the half now, folks. So I'm going to get 2. I'm going to get 9 O2s. I'm going to get 16 carbons and 18 waters. Obviously, in an exam, I'd clean it up, make it a bit better. There we go. Next, question number 2. Question number 2 is done. So question number 3, incomplete combustion of propane to form a toxic gas. Okay, oh, that's clever. So we've got propane, nice word equation. Propane. Oh, I don't know what propane is. Toxic gas. Carbon monoxide and water. Balanced equation. C3H, it's an ane, double it and add 2. Con! Yo, God, you made it! Good man. There he is. Just missing Eura now. Oh, we miss you, Eura. Double it and add 2, 6, 8. Plus O2 goes to CO plus H2O. Balance it. Go away, keyboard. So I've got 3 carbons, 8 hydrogens, 4 times 2. Oxygens, 3, 4, 7, divided by 2, 3.5, double everything. 2, 7, 6, 8, and I'm done. Question number 4. Let's see how quick I can do these. Complete combustion of butane. Right, so butane plus oxygen goes to complete carbon dioxide and water. Right, complete combustion, C4, double it and add 2, 8, 10 plus O2 goes to CO2. Come on. Do you know what? Going too fast actually slows you down. Balance it, 4 carbons, 10 hydrogens, 8 plus 5, 13. 13 divided by 2 is 6.5. Double everything. Eura's here. Oh, hey, Eura, did you make it? Oh, I'm so glad Eura's here. I'll do the red. Well done, Eura. It's good to see you. Double everything. 2 plus, that was 13 oxygens, plus 8, plus, 10. Yeah, done. Like it. Right, the next one was, what was the next one? Oh my goodness. Hexadecane. How many of you guys had to look that guy up? C16, H, double it, 32 plus 2, 34. Holy mackerel. Guys, can I just do the symbol for this? It's going to take me too long. Did it say complete? Said complete. So I'm going to make CO2 and water. By the way, hexadecane, for anybody who's interested, that's diesel. That's what that is. It's kind of cool, that. Kind of cool. Octane spectral. Had to make sure. Okay, balance. 60. Oh, no, it's a lot of carbons. Hydrogens. Oh, no. I don't know what fave. What about 17? 17 oxygens. Holy moly. 32 plus 17. 49. Divide that by 2. 24.5. Right, double everything. Holy mackerel, this is a big equation. 2, 49, 32, 34. Wow, that's a toughie, that one. That was a big one. Next, complete combustion of propane. I like this. They keep, I don't mind the repetitive nature of this. Complete combustion, of course, is always about that max energy output. Was this propane again? Is this propane? I see propane. Yeah, propane. C3H6 add 2, 8 plus O2 goes to CO2 plus H2O. Maximum energy output. This is why we love complete combustion. Remember, it's all about energy. So we need 3 carbons, 8 hydrogens, 8 hydrogens, oxygens, 6 plus 4, 10, 5. I'm done. No doubling it. Whoo! Thank goodness. Word equation. Propane plus oxygen goes to carbon dioxide and water. Incomplete combustion of ethane to produce global dimming. That's clever. Ooh. Was that ethane? It was, wasn't it? C2H4 add 2, 6 plus O2. So ethane plus oxygen causing global dimming. Carbon particulates and water. There we go. Balance it. 2 carbons, hydrogens 3. So there's 3 oxygens there. Sorry, hydrogen 6, hydrogen 6, oxygens 3. I need 1.5 of those, but I then need to double everybody again. Double it, double it, double it, double it, and I'm done. Yay! Wow. So how long did that take me, by the way? I've been streaming 11 minutes, I think. Have I been streaming 11 minutes? Really? Oh, cool. So it took me 11 minutes to do the homework, although I haven't done the words for all of them. I apologize. Right, and partly the reason why I want to do that is so I can then crack on with moles. So today, guys, our title is moles. Yay! We're gonna look at some moles. Gonna look at some moles. Gonna look at some moles. Moles. There we go. I've done as a moley. I don't like his hand there. His hand's rubbish. No, that was rubbish too. Oh no, what is wrong with me today? There we go. Moley. We've got a chemistry mole, folks, is what that is. It's a chemistry mole. And I shall call him Moley. Yeah, there we go. So the question is, what has moles got to do with chemistry? So my learning objectives are, I need you to understand the unit of the mole. The mole. There we go. Understand the unit. Next, I need you to be able to use an equation, which is N. And by the way, N is the symbol for moles. So N equals moles equals grams over rams. This is how I teach it, folks. I just find it easier this way. Some of the teachers you will definitely hear, it's so cute, it's hands. So grams over rams. You might also hear mass over MR. Yeah, you might also hear that one. You can choose whichever one you want. The last one is I need you to be able to rearrange. So this is not complicated today, folks. But the first bit is complicated, the unit of the mole. So the first thing I think I want to do is I need to do the bit of the history lesson here, folks. So where does the word mole come from? So the word mole comes from the word, and I think I wonder if anybody actually knows already. Does anyone know where the word mole comes from in chemistry? It comes from the word molecules. Kind of makes sense, that. So what they needed to do is scientists and chemists have been describing substances in terms of molecules for hundreds of years. Yeah, well done, Ashley. Well done. Aye. Nice, Ash. Yeah. So it comes from the word molecules, and it has one function. So what is the purpose? Question. What is a mole? And writing down that it's a furry creature that lives on the ground, definitely. The name mole is an 1897 translation from the German unit mole, coined by the chemist Wilhelm Ostwald in 1895 for the German word molecule. Wow, check you out, Roo. Smashed it. There we go. What is a mole? A fixed known number. A fixed known, I won't do the shortcut bit. Fixed known number of particles. I'll put a fixed known number of molecules. Why not? What's wrong? My brain's faster than my hand. There we go. A fixed known number of molecules. Now at that point, people go, I don't get it. They're like, I don't understand. What's it used for? So question. What is a mole used for? Different question. What is a mole used for? The answer is to count particles. And that is something which students kind of go, okay, so why did they need to invent a unit to count particles? And that's another really good question. So let's write that one down. So why the mole? Why the mole, question mark? Why is counting particles or molecules? I actually prefer particles in this case because the word particles incorporates atoms and molecules. Yeah. Why is counting particles hard? Whoop. There we go. Why is counting particles hard? Question mark. And I think most people would understand this. That's because the answer is molecules are tiny. Particles are tiny. Isn't this, look at the irony. I wrote tiny and big. see words. I'll stop. Doing the same, you're doing less. I'm such a dad. I'm a dad, but not a dad. It's such a dad job. Sorry. Forgive me, folks. I'm sorry. Particles are tiny. Like really, really tiny, folks. Like crazy tiny. Like so crazy tiny. I'm tempted to actually give you some sizes if you like. But the problem is because particles are so very tiny, just so you know, molecules often measured, they're so small, they're often measured on the picometer scale. How crazy is that? The picometer. So just to give you some idea of sizes, top-notch comedy here. Thanks, Harris. I'm going to take it that sarcasm. It's so upsetting. It's really so hard on these lessons to be funny. You know what the funny thing is? I actually don't really try to be funny. It's just chemistry, you know. Molecules often measured in pico. Just to give you an idea of what that is, 1 meter is the same as 100 centimeters, which is the same as 1,000 millimeters. Do you know what? I shouldn't go in that direction. I shouldn't go in that. What I'll do is, I don't like that direction. I prefer to go 0.01 is a centimeter. That's a what I'm doing is, guys, I'm just comparing this to the original meter. So what's a millimeter? A millimeter is 1,000th of a meter. Yeah, we kind of get this. It's 1,000th. So then we go to micrometer, which is kind of cool. And this is what the microscope was designed to read. Oh, have I gone too far? Gone too far. There we go. By the way, 10 to the minus 6, 10 to the minus 3, 10 to the minus 2 for centimeters. Yeah? I somehow found it funny, not going to lie. Thanks, Ben. Thanks. Where Mr. Duncan has a breakdown. It's possible, Shan. And I am talking about moles here. I mean, I drew a mole, Shan. I drew a mole. There is a chance I may just go into complete meltdown at some point. I don't really quite know what's going on anymore. So we're now at the micrometer. Now we need to go to the nanometer. Nanometer, really tiny, like super tiny. There you go. 10 to the minus 9. That's really, really small, folks. Just to tell you, that mole is cute. I know. So just to give you a kind of idea of those scales. So I'm trying to think. So centimeters would be like, I don't know. We need to, so this is like this is how you'd measure a calculator. Yeah, calculator. There's a calculator. So you'd measure a calculator with its little buttons and its screen. Yeah, and it would be in centimeters. Well, what would you measure in millimeters would be like a rice grain. It's nice to give you these kind of stats. So a little baby rice grain, which you'd measure in millimeters. And then what? Now we get down to micro. So micro is cells. So like a plant cell with its vacuole, its nucleus. Yeah, so this is a cell. So cell you measure on the micro scale. Yeah, we're going to be measuring that on the micro. So that's going to be the micrometer. So what happens? Oh, Donna, could you grab me the battery? So the next question is like, so molecule. Oh, Roo, that's amazing. I've never used that, but I am going to from now on. So the question is, how far do we now get to nano? So nano is like, just to point out, like it's getting now crazy tiny. We're talking about viruses. We're talking about the coronavirus here now, folks. Yeah, we're talking about the viruses are on the nano scale. Yeah, a virus. They're tiny. Yeah, nanometer. They're like 230 nanometers. Or if you want it in meters, times 10 to the minus 9 meters. Crazy tiny. And then you go to the picometer. Picometer's another 1,000 smaller. I mean, guys, this is like super tiny. Like, how is it even possible to know these things even exist? Times 10 to the minus 12. Like, that'd be crazy. And by the time you're getting down to this, you're measuring water molecules. Yeah, you're measuring molecules now at this size. Yeah, these are way smaller than viruses. Pico. Yep. So it's kind of cool to kind of understand those kind of scales and kind of see what we're kind of measuring here. But it is just, they're so small you can't measure them. So one of the really classic examples of this. So if I were to have a glass of water, I'm going to be using this analogy quite a lot this lesson. So if I have a glass of water, and in that glass of water, of course, I've got H2O. Well, if I were to zoom in, if I were to pick a spot and zoom into the picometer scale, I'm going to see all of these billions and billions and billions and billions of water molecules. Yeah, there's just going to be so many. So how many molecules are in a glass of water? Well, in one glass of water, there are more molecules of H2O than there are glasses of water on the whole planet. So that can be a little bit planet. There you go, planet. So just to kind of reiterate, what it's kind of saying is, if you were to take the Earth, and you're going to take all of its oceans, yeah, is Europe over here somewhere, stuff like that, and you take all of the oceans, and you take every drop of water in these oceans, and you put them into cups, yeah. There is more molecules of water in one glass than there is cups on the entire planet. They're that small. It's crazy. So what this meant was they couldn't count them. It would be madness to count them. So how do you count something when the numbers are so massive? Now, the next bit is amazing. This is like standing on the shoulders of giants, crazy, crazy smart. What they did is they invented the mole. They said, well, every molecule has a different, molecular mass, relative molecular mass. So just to keep that simple, they said that every molecule's got a different mass. Water, which we've now done, and we did this in lesson, yeah, water, hydrogen is 1, oxygen is 16, water has a relative mass of 18. Oxygen gas has a relative mass of 32 because it was 16 times 2. Hydrogen has a relative mass of 2. Yeah, it's tiny. Hey, hydrogen, you're really small. You're really light. Let's go for something bigger. Let's go for glucose. Love glucose. Glucose, 180. So we've got 12 times 6 plus 1 times 12 plus 16 times 6, 180. So would everyone agree that because the particles all have different compared masses, they came up with a genius solution? So what is 1 mole? And they made a decision, folks. They made a decision. 1 mole is a substance's AR/MR, relative molecular mass or relative atomic mass in grams. That's super clever, because what that says is that if I got given 18 grams of water, that because those particles are, let's say, hydrogen, are 9 times heavier than hydrogen, if I just have 9 times the mass of it, then I'm going to have the same number of particles. It was genius, like crazy genius. How do we make sure we get the same number of particles of everybody? You just weigh out their mass in grams. And it was like the leap of faith that took was enormous, but it really, really clever. And this means it actually creates an equation. They said, so the equation, 1 mole equals the mass over its relative molecular mass. So I'll put brackets RMM. So we've got, this is glucose. For 1 mole of glucose, I just need 180 grams because its relative mass is 180. And they created an equation, number of moles, and N is the symbol for moles. But by the way, if you actually spit out moles as an answer, you have to just put mole, which is really stupid, I know, go figure. Moles equals grams over rams. Okay, so now, I'm going to put a question out here now. There's a good chance that no one is actually thinking it, but I'm going to do it anyway. So there was a really, really famous scientist, a very famous scientist that came along in the early 1900s and asked a question. 1 mole, we had been using it for hundreds of years. The question was, how many particles are actually in it? Because no one actually knew. They didn't have a clue how many particles it was. They just said, we can just call this our unit number 1. We just weigh out the molecule's mass in grams. I don't know how many it's going to be. Does anybody in the room want to guess which scientist was the first person to give an answer to that question? A very, very, very famous scientist, folks. Very famous. I wonder if anyone's going to know. I'm just waiting on the chat to see if anybody does. Come on, a very famous scientist is the right answer, Ashley. It was Einstein. Yeah. So Einstein, can you believe that? Like, this is my unit. I own this unit. This unit is for chemists. Yeah. This is the chemistry unit. Yeah. It's mine. This is Mr. Duncan's unit. I own this. And then the person who actually figured it out was Einstein. Duh, physicists. Ugh. So anyway, he did some really cool experiment. He actually read a paper, a French scientific paper written about 60 years earlier, describing the motion of pollen grains on water. And he actually managed to calculate how big the molecules were that were hitting the pollen grains to make them vibrate. They were like floating on water. It's a cool experiment. If you're interested, look it up. But the answer to that question, so how many particles are there, is this. I'm gonna make my pen fatter. This is a big moment. 6.022 times 10 to the 23 particles. And this is now called, did you know they actually contemplated calling this the Einstein constant, but then the chemists got mad. Lol. And Einstein didn't actually give that number, by the way. Einstein's number was like 4.27 times 10 to the 23. It was a really good effort, like an amazingly good effort at that. And then another famous chemist who then improved it. And so this is now called, this number is called Avogadro's number. They gave it to him. Yeah. So this is the number of particles in 1 mole. Okay, so the next question is, so how is this useful? So we're just going to do a couple of questions because we need to reorganize an equation in a minute as well. So I'm just going to then, let's start having a look at, I have no idea what I pressed here, folks. There we go. I got rid of it. No, I haven't. Let's come back. Okay. Let's get rid of that. Okay. So let's put this now into practice. So I'm trying to zoom into like kind of, okay. So questions. Question number, whoa, that's very thin. Question number 1. It's still really thin. I don't like it. Let's make it thicker. Q1. Cool. So question number 1, I'm going to give you 36 grams of H2O. Question, how many moles do I have? And therefore, so moles, number of moles, number of particles. Right, you guys can have a go at that one. There we go. Okay, so here's my equation. Number of moles is grams over rams. Right, input my data. Number of moles, grams is 36. How much does water weigh? Yeah. Oh, Kieran asks, how many of what sort of particle? Oh, from Einstein. He actually counted the number of water molecules in 1 mole. He put water onto a petri dish, sprinkled on some pollen grain, looked under it under a microscope, and the pollen grains appeared to vibrate. Now, what he then did was he knew the weight of the pollen grains by he'd weigh the flour, then he'd sprinkle on the pollen grains, then he'd do the mass difference to work out the exact mass of pollen. Then what he does now, pollen grains do something really cool when they go into water is they spread out evenly so they're no longer touching. So you actually separated them into individuals. He then knew the magnification of the microscope, and he was looking at a spherical area, and he counted the number of particles, the number of pollen grains in that. Therefore, he could work out the actual mass of a single pollen grain. Then he looked at how much it was vibrating. So he calculated the energy that was required to make the pollen grain move by that amount. Therefore, he could infer the energy from the temperature, and then he could work out the inertia by the energy and the mass of the water particle in order to create that kind of collision. It was amazing. Genius. Honestly, Einstein. Bonkers clever. So, how much does water weigh? Hydrogen weighs 1 on the periodic table. Oxygen, of course, weighs 16 on the periodic table. There's 2 hydrogens. So water weighs 18, of course. So water weighs 18, which is the MR of water. So I now get a number of moles is 2, I think. 36 divided by 18. Sorry, I just don't trust myself. Yeah, 2. And therefore, what's the number of particles? So we know that 1 mole equals 6.022 times 10 to the 23. Therefore, if I've got 2 moles, I'm just going to times it by 2. Yeah, 2 moles is going to be twice that, times 2. So I'm going to do 6.022 exponential 23 multiplied by 2, and I get 1.204 times 10 to the 24. There we go. It's the actual number of molecules that I have. How? I know, Shan, don't worry about it. Like, I'm happy to do, I could chat to you about Einstein's genius anytime, but I won't bother. But it's really clever. It's like super genius, Amazing. Right, let's go question number 2, folks. Same thing, number of moles, number of particles. Right, so question number 2. I'm going to give you 330 grams of water. And the reason why is because this is how much is in the average glass of water. Figured we may as well do that. So, give me the moles, number of moles, and give me the number of particles. Particles. Guys, so in the average glass of water, you're about to work out the actual number of particles of H2O that are entering your body. How mental is that? So cool. So cool. Chemistry, so cool. Isabel, why would we need to know the number of particles in a substance? Isabel, don't forget that question. That is the big question, isn't it? Why would we even care about this? Isabel, I'm about to blow your mind. It's going to be amazing. You just wait. So, number of moles of water. So, the process, number of moles is grams over rands. Right. Put my data on. 330 over, what does water weigh again? 18. So I'm going to do 330 divided by 18. Gives me a number of 18.3. It's actually 0.3. There we go. 3 sig fig for chemistry. Number of particles. I'm now going to take 18.333 and multiply that by Avogadro's number. Oh, sorry. I mean Avogadro's number. Oh my God, can you imagine that many avocados? Oh my God, I'd have so much guacamole. Oh, it'd be so good. Love guacamole. It's amazing. 18, I'm actually going to use the answer on my calculator. Multiplied by 0.22 exponential 23. There we go. That means I'm going to have, the answer is 1.10 times 10 to the power of 25. That is a lot of molecules, that, folks. That is a lot of molecules. Like, woza, a lot of molecules. All that in a glass of water. Amazing. Right. Okay. I can't ignore Isabel's question. This is now going to blow your little child minds. It's going to be amazing. Are you ready? Okay. So why would we care? Isabel, can I ask a question for you? Can you give me something to build in chemistry? Give me your favorite chemical compound. Just your favorite one. I really hope it's a good one, Isabel. Make it funny. Come on. Oh, I've never heard of I don't know what that is. Diamond. Oh, no, it's not a compound. That's an element. That's carbon. You're absolutely right, Isabel. Give me a compound, something fun. Name something. Name a compound you eat, Isabel. This is great fun. I'm really enjoying this. I feel like I'm still managing to bully Isabel, even over YouTube. It's amazing. Thank you. Glucose, right. So Isabel's going for the typical student answer. Actually, it's actually not typical, but sugar. I like it. We're going to make glucose. Because let's be fair, Isabel. Let's go for, I'm going to make my pen a bit. Glucose. There we go. Glucose. So Isabel wants to eat this stuff. Glucose is awesome. It's delicious. It's sweet. And you can buy it from the shops. But let's be fair. I'm a chemist. I'm going to build it. We're going to make glucose. So if I want to make it, it needs to be on this side of the equation. Right, so we're going to build glucose, and we're going to build it in chemistry. Isabel, what elements do I need to go to the shop and buy? Go. Yep, thank you. Carbon, and? Yep, thank you so much, you star. It's really nice to remind ourselves, any element that ends in gen or ene is diatomic. So I'm going to go to the shop and I'm going to buy some elements, some carbon, some hydrogen, some oxygen. I've got carbon as a solid, hydrogen as a gas, an explosive gas, oxygen as a gas. Right, Isabel, how much sugar do you want me to make? Give me it in grams. How much sugar do you want to eat, Isabel? By the way, just to tell you, glucose isn't actually sugar. Sugar is actually sucrose, which is a disaccharide. Oh, cool. But glucose, you can actually buy glucose, by the way. If anybody has diabetes. It causes diabetes. If anyone has, oh no. Is it diabetes? It is type 1 diabetes. Yeah. If they have type 1 diabetes, then they have to balance their glucose levels themselves. Anyway, and you can get glucose tablets. So Isabel wants me to make 200 grams of glucose. So Isabel, how much carbon and oxygen and hydrogen do I need to buy? Let's see what she says. I'm hoping she's just going to write times by 200. Nope. Okay. Are you ready for the magic, Isabel? Okay. Here's how it's going to work, right? We need 200 grams of glucose. The first thing I think we ought to do is we need to balance the equation. It's the first thing we do in chemistry. So we've got to, I'm actually going to move my equation hang on. I'm just going to move my equation over a bit to give me a bit more space. There we go. So I need to balance my equation. I need 6 carbons, 6 carbons. I need 12 hydrogens. I need 12 hydrogens. I need 6 oxygens, 6 oxygens. Is everyone okay with that? So now that I've got my balanced equation, now you guys have been balancing equations for literally probably a year now, maybe even longer. And here's a question for you. Why do we balance equations? The reason why we balance, so I'm going to give you a minute to answer that. Because there's a GCSE answer and then there's an A-level answer. Why do we balance? Why do we balance equations? Why do we balance equations? Number one, I'm hoping that you guys would tell me conservation of mass. My pen's hiccuping. That's not a good sign. It did this before. Conservation of mass. Well done, Ruby. You star. Ruby, that was a great answer. Have a commendation. Have 3. That was amazing. Well done. That's not why we actually balance it. That's just common sense. Yeah, that's not why we balance. That's just common sense, folks. I mean, come on. Oh, no. My laptop's doing weird things. Oh. That's just common sense. I'll write a bit more slowly. The real reason is because we want a molecule ratio. Because what does the equation actually say? It says 6 carbons react with 6 molecules of carbon react with 6 molecules of hydrogen, will react with 3 molecules of oxygen and make 1 molecule of glucose. Right. So now that we know how many molecules we need to make 1, now we can make 200 grams of it. So the question now is, how many molecules does Isabel want me to build? How many moles does she want me to build? She wants me to build 200 grams worth. Number of moles is grams over rams. Right, number of molecules is 200 grams over 180, the relative molecular mass of glucose. So 200 divided by 180. She wants me to make 1.111 moles, I'll put molecules of glucose. Well, if we now realize that 3 oxygens are needed to make 1 of them, how many oxygens did I need to make that many? Well, to go from here to here is times by 3. So I can times that by 3. I times it by 3. I need 3.333 moles of oxygen. I've got 6 minutes to sum up this lesson. Next, that's the oxygen I need. How much hydrogen do I need? To make 1, I needed 6. That's a times 6. We've done the times 3 for oxygen. Now we need to do the times 6. So we're going to multiply that up by 6, which is 6.666. This is going well. Next, how many molecules of carbon did I need? I also needed the same number as I did hydrogen, 6.666. Right. Now here's the magic. Moles are no use to a chemist in a shop. If I go into a shop and I ask them to give me 6.66 moles of carbon, the guy's going to look at me in a very funny way. We need to reorganize this equation. Grams over rams. Reorganize it for grams. Bring the rams over. I don't know why my laptop is being silly. So number of moles times by rams will give me grams. Right. How much does carbon weigh? It weighs 12. My apologies. It weighs 12. How much does oxygen weigh? Well, oxygen is in O2, so it's 16 times 2. It weighs 32. How much did hydrogen weigh? Hydrogen, of course, weighs 2 because it's 1 times 2. Oh, I've put them in the wrong place. Put them in the wrong place. I went up to check. That's why I did it. Carbon's 12. Hydrogen weighs 2. And oxygen weighs 32. Oh, if I'd got that wrong, I would have had a very different set of numbers. Right. Guys, watch the magic. So, are you ready? 12 times 6.666. I get 80 grams. Look, hydrogen, 2 times 6.666. I get 13.3 grams. I get oxygen, 32 times 3.333. I get 106.7 grams. Guys, what does all of that add up to? Isn't it magic? And that's exactly how much of each one I need to buy as a chemist. Isn't it magic, Ruby? Isn't it magic? Oh, I love chemistry. And that brings me to the end of my lesson. It was amazing. Oh, right. Okay, guys, hang on. I'm just going to turn my camera back on. Enable. Then go to this. Then I'm going to go stop screen, stop sharing. I want to go that guy. And then start cam. Amazing. Hey, guys. How amazing is chemistry? It's like full magic. We can calculate now exactly how much we need to get to build everything in the universe. I can even put together a list of all the stuff I need to build Toby. I know, magic, right? Anyway, guys, I will post on the classroom just a quick worksheet for you to have a go at calculating moles, and it will just be using grams over rams and rearranging it. It has been amazing to see you guys, as always. I hope you're all looking after each other and having a nice day and being safe, and hopefully I'll see you soon. Guys, I'll see you next lesson. Have a great day. See you later.